So, hello everybody. I am very honored to be here to talk about John Nash's contribution 75 years ago and to meet all of you and discuss game theory. It has been a long time, 75 years, and as we have heard also the developments, I will refer to some very old and basic questions that arose already in the beginning. And I will not do any fancy things. I was very impressed by Rida's presentation, for example. It's a very beautiful generalization and extension of Nash's ideas. We will just look at some basic questions about Nash equilibria. And this is joint work with Erik van Damme, who you may recall from his book on stability of Nash equilibria and things like that. And Erik and I have worked on different topics. Now we took up an old topic to examine together, and we came up with a criterion on Nash equilibria, which we call detection stability. So I will talk about something basic here today. So first of all, when it comes to mixed equilibria, and I talk about finite games now, there are three major interpretations. Well, the classical one is that these are deliberate randomizations made by the players, and that is how it was thought also by Emil Borel, who was the first to define mixed equilibria and mixed strategies, I should say, and then von Neumann in 1928. Then came John Nash, and in 1950 he wrote his one-page paper, which we just heard about, but also a PhD thesis in mathematics at Princeton. In that paper, which was actually not very mathematically rich, so John Nash himself was not very happy. He wanted to add more things to his thesis. But his advisor was Tucker. Tucker was the chairman of the math department of Princeton. And said, this is such an innovative idea, you should just write it up and also publish it, which he did, and then wrote this. And then when he wrote this paper, which is unpublished, he gave two interpretations of Nash equilibrium. One is in line with what we would think of as this deliberate randomization and rationality and so on. But another one was this mass action interpretation, which was referred to earlier here, where he imagined then large populations of individuals in the different player roles, so one player population for each role of the game, as he called them. And these guys then would then be randomly drawn to play, so they would meet people from other populations and play in their roles, and they would learn something empirical about the payoffs they earned when they met, and then it's your turn to play, and you look at those payoffs and you try to avoid suboptimal strategies. And he didn't formalize this. He thought of this as a stochastic process, and then he said that if this has a stationary distribution, so it reaches a stationary state, so it just reiterates itself, then we can look at the distributions over the actions taken or the pure strategies used by these people. They only play pure strategies, and think of them as mixed strategies. So mixed strategy then is just a statistical distribution of pure strategies, and people only use pure strategies. And he said, if that is stationary, it should be a Nash equilibrium. People have avoided the suboptimal strategies. So in that case, there is no deliberate randomization, but people use pure strategies. And then came also John Harsanyi with the Bayesian interpretation of a mixed equilibrium, that people actually don't mix, they don't randomize, but my mixed strategy is your belief about what pure strategy I will take. And he worked on this idea in several contexts. Now that has been developed then later by Aumann and Brandenburger, the Bayesian understanding. Okay, but in this, thank you. But in this study, we will stick now to the classical interpretation and to see then, examine more carefully what about mixed strategies in that interpretation, when it's deliberate randomization. And we take this to be the leading interpretation when you teach game theory. And let me see here, I want to, there we are. Okay, I'm sorry for that. Okay, so just a quote from von Neumann and Morgenstern in their book. In playing matching pennies against an at least moderately intelligent opponent, the player will concentrate on avoiding having his own intention found out. This was a rationale for using a mixed strategy to randomize among the pure strategies. Schelling, in 1960, in his book, wrote that the essence of randomization in a two-person zero-sum game is to preclude the adversary from gaining intelligence about one's mode of play. In games that mix conflict with common interest, however, randomization plays no such central role. So these were thoughts about mixed strategies. Now, as teachers of game theory, as many of you are here in this room also, you usually experience that students are a bit skeptical about mixed strategies, maybe except for zero-sum games and games like that. It seems rather natural that you randomize. You don't want to play pure strategy. And one thing that they find paradoxical is that you adapt your probabilities in a mixed equilibrium to the payoffs of the other guy. And indeed, in experiments with certain non-zero-sum games, one has found that there is an own payoff effect. So you change the payoffs of this player himself, and that shouldn't affect him in equilibrium, but actually he will change his probabilities. So there is an own payoff effect. Now in sports, in tennis and such other sports, one has also looked at this, and there is more of a tendency to actually be closer to mixed equilibrium than in these experiments. I'm sorry?
Sports is usually zero-sum.
Yes, yeah, that's true. Now, another thing is that students are uneasy about the fact that in an equilibrium, if you are supposed to use a mixed strategy, why would you play exactly that? Why should I play that strategy? Well, if I use that, and that would be known by the other player will be indifferent and hence want to randomize, so that can justify it. But why would I care about that when I play it? I just played once now. I could play anything that is the best reply. Why don't I use one of the pure strategies in the support of my mixed strategy that I'm supposed to play, or randomize uniformly or do something else? So that leads me to the question that we address here, which is a limited question and much basic question. So in what situations does a player have an incentive to use her equilibrium strategy if there is a small probability of detection that the other guy will find out? So I think of two-player games now, and suppose there is a small risk that my strategy is found out, pure or mixed. So it means if I have a pure strategy, it's rather simple. If I have a mixed strategy, it is as if somebody has found out. I will randomize in this way when I play the game. And that is a different revelation than the revelation of a realization of a mixed strategy, right? Which is another topic, and I will refer to that later on. This was studied by Arthur Robson. Now, this is a thought experiment. So what happens if I'm worried that maybe my pure or mixed strategy will be found out before I just play the game? And those equilibria that provide such incentives, which I will make precise, we call them detection stable. Okay, that was the title of the talk. So detection stable equilibria, or DSE. So we're not the first to argue that some mixed equilibria in some games are not so convincing. Aumann Marschler, in paper 72, thought about that, related it to max-min strategies. I will talk about that example they had. And Harsan, as I mentioned, also was discussing this in terms of in a book also where he's discussed what if a game is such that the Nash equilibrium does not achieve a higher payoff than max-mining and so on. And he was then recommending max-min instead of Nash. Rosenthal wrote a paper about commitment-robust equilibrium, an idea that said, well, actually, when we say simultaneous move game, it's never exactly simultaneous, and sometimes the player can actually force and go ahead and commit to a strategy before the other player. What if there is a risk of that? We want the robustness of that. That was what Bob Rosenthal was looking at. Arthur Robson looked at informational robust equilibrium when the realization of a mixed strategy might be detected by the other player. So I will relate briefly to those. Now, Aumann and Marschler then talked about Nash equilibrium compared with min-maxing. And they were considering a non-zero-sum game where there was a tension there. And then they said about that game, to be sure, we do not know what to recommend in this situation because the max-min strategies are not in equilibrium. It was not zero-sum. But the max-min strategies can certainly seem preferable to the equilibrium strategies in that game. Now, if we apply our machinery to their example, we will find that that equilibrium, which is unique, is not detection stable. So now you see already we don't have existence in all games, right? So some games will not have any detection stable equilibrium. And if we relate it now to what I mentioned before, then we see here that detection stability is intermediate. Lies here. This is the commitment robustness of Rosenthal. That's a subset of our set of equilibria, which is a subset of those that Arthur Robson looked at, informational robustness. So it's in between those two. in terms of strength. Okay, so the rest of the talk will be, I will give you the definition and basic properties, some examples, then I will characterize this criterion for stability in terms of a two-stage game, which is like a spying scenario, where people can spy on each other, and apply the concept to zero-sum games, strictly competitive games, and potential games, and conclude. So that is the plan of the rest of the talk. So any questions so far? Oh, okay. So the definitions now. The domain of analysis now is just finite two-player games. And the notation will be the standard one, so capital S will be the set of pure strategy pairs or profiles, and U will be the payoff function that maps to payoffs to the two players, and we will assume, as usual, that these payoff functions can be derived from some underlying preferences on the pairs of pure strategies that meet von Neumann-Morgenstern axioms. So we have standard preferences here. And I'm sorry for the instability of my. It is. Yeah, it's not very stable. My way of handling this. There we are. So now if we have the notation clear, the definition is very simple. It's given here. So take a Nash equilibrium sigma star in pure mixed strategies in the game, a finite two-player game. And then you say, let's look at all best replies that player I has against this equilibrium. So if the player expects the other to adhere to the equilibrium, what are my best replies? And then we require this inequality hold. Okay, what does it say? It says it should not be the case that there is a best reply such that if I would choose that instead, and that would be detected by the adversary, then I would be sure to get a higher payoff than equilibrium. So if he discovers this and plays the best reply to that, then I would actually gain. Okay, so there shouldn't exist an alternative best reply such that if detected, it would lead me to a higher payoff. Now that is one way of formalizing this idea, and we have a weak version and a strong version also, which I will not tire you with, but I will mention it briefly at the end.
What does sigma I appear in equation 1? Say for all sigma I and beta I. I don't see any sigma I in equation 1.
Yes, you look at the other guy's best replies against sigma I.
Oh, instead of sigma, you mean UI of sigma I, sigma j. That's what you mean. Okay. Sigma I star. Okay. Got it. The sigma then, UI of sigma, you mean UI of sigma I, the one that you assume in beta I of sigma star, and sigma j, which is the thing you make minimum of. Correct?
You pick a sigma, yes, you pick a sigma I.
Which is the best reply to the equilibrium.
Right, and then it should be sigma, yes, and then my payoff, I'm player I choose another best reply sigma I, and sigma star I is the player strategy, right? And then this says if the other player chooses sigma j and plays the best reply against my sigma I, then I have chosen sigma I, he chooses sigma j, then my payoff is not higher. So sigma consists of sigma I and sigma j, sigma 1 and sigma 2. So there is sigma star, okay? And we think of player I. Player I thinks of an alternative best reply sigma I. And then you say, okay, the other guy can then choose sigma j if he would discover it, right? And then my payoff would be ui of sigma, my sigma I and the other guy's sigma j. I think if I give an example, it would be easier. The contents is, there shouldn't exist an alternative best reply, such as if the other guy best replies to that, then I will earn a higher payoff.
Shouldn't then the min be a max?
That's what I said. We have versions of this which are weaker and stronger, so I will talk about this version. Yeah. So let me look at examples and you will see it. If the notation is not so clear, I'm sorry for that. But if you look at this definition, then if you plug in for sigma here, in this inequality there, it's met by strict equilibria. So strict equilibria have this property. And let us look at examples. So let's start with the matching pennies game, which has a unique Nash equilibrium, uniform randomization, and that will be detection stable. Why? Well, if I would play my strategy, I would expect a payoff of 0. Suppose I would play something else than that, for example, a pure strategy or another mixed strategy, and that were discovered by the other guy, then the other guy would respond with the pure strategy, and I would earn a lower expected payoff. Right? So that so that would then meet the criteria, and there's nothing that could give me a higher payoff. I want to hide my strategy, just as von Neumann said, and Borel and so on. Now look at this coordination game where it is not the case. So it has 3 Nash equilibria, right? One is the good Nash equilibrium, a strict equilibrium AA, where they have high payoffs. The other one is a strict equilibrium 2, so both are detection stable. However, there is a mixed equilibrium, which is 1/3, 2/3, and that is not detection stable. Why? Because if I'm supposed to play then this mixed equilibrium strategy, 1/3, 2/3, I could do that, and then I will be indifferent between, I will be, I can choose anything. If I expect the other guy to play his part, I can play anything. And if I would use some other strategy than 1/3, 2/3, for example, playing A for sure, I would be just happy if the other guy would discover it. I would earn a higher payoff. So it's not detection stable. So here we agree with Rida's talk, that we would reject the mixed equilibrium here, right, for other reasons. Any question there?
Two quick questions, please. The first one in the definition is sigma needs to be a best response to?
Yeah, we look only at best responses. So you are exactly. So with best response within your set of best responses, why should I choose the best response I'm supposed to play?
Okay. My second comment is, can't you apply this to more general profiles, not just Nash equilibria?
One could possibly do that. We thought that this has been so little studied, this scenario, so we want to make it careful in the most clear case we can think of. 2-player games, finite, and Nash equilibria, right? And the risk of being discovered. Now, if you take this mixed equilibrium here, so that meets all the refinements, standard refinements, like perfection, properness, and stability, but it is not accepted by this solution, as was the case in Rida's talk also. Yep.
In a sense, you're saying you may want to be discovered even though you suffer a loss in the short run because you would benefit in the long run. I know you haven't been speaking about repeating.
But let's think about it once more. So if suppose you are playing this game and you're expecting the other guy to play the mixed equilibrium strategy and you are also supposed to do that, then you say, why should I do that? Maybe if there is a small risk that the other guy will discover what I'm doing before we play. Now, if you would play your mixed strategy, you could do that. You could play anything else, and if the other guy doesn't change anything, then you are happy. You just earn the same expected payoff for anything you play. Everything is the best reply. And then it says, well, if I then would play this, and there is a possibility the other guy discovers it, it's maybe better for me to play something else, for example, A. Thank you. And here's the Maschler and Aumann and Maschler example. This is a non-zero-sum game. It's like a matching pennies, but you see the payoffs are 0 and 1, but there is 1, 3 there. So it's not zero-sum. And it has a unique Nash equilibrium where the first player randomizes 3/4, 1/4 to keep the other guy indifferent, and the second player 50-50 to keep the first player indifferent. And then Aumann and Maschler say that this is not a plausible strategy to use, the equilibrium strategy, because they could play min-max and be sure to get the equilibrium payoff. Why would they play this? Now, in our machinery, we have this detection stability idea. So that I wanted to show you this graph because this is how it's thought about, and maybe that responds to the obscure maybe notation that I will look over. Because this says, suppose you are player 1, and now you are expecting the other guy to play this equilibrium strategy, right? And then you think about, okay, all these things are our best replies. I can assign any probability I like to pure strategy T. But now suppose, in this scenario, that the other guy will find out my strategy and best reply to it. Well, if I choose a lower probability than the equilibrium probability, so it's low probability for T, then the guy will choose L, right? And that means that my payoff will increase with my probability of playing T linearly up to the point where I reach the equilibrium, where there will be indifference. The other guy will be indifferent and can play anything then. And that means that my payoff can vary from the Nash equilibrium payoff of 1/2 here up to 3/4 or down to 1/4. If I increase further my probability, he will switch to R, and my payoff will be declining. So if you think of this, that player 1 thinks, okay, I might do something, and if I'm not discovered, and I play any one of the strategies, my expected payoff is equilibrium payoff. However, if I play something this and the other here, and the other guy discovers this, I might benefit. So if I would play something in between here, I would earn a higher payoff. So there are profitable deviations if they will be discovered. So this is not detection stable. Okay, so this is a kind of second order calculation. Now, if one looks at this definition and examples, one can easily verify it's logically independent from other refinements. So there's nothing that does this thing. Now, what about writing up an extensive form game, or a two-stage game it will be, which implements this scenario of discovery? So we wanted to do that to be clear. And in this spy scenario, you start with any finite two-player game G, and then you choose some numbers epsilon1 and epsilon2 that are small, positive. These are the risk of being discovered for the two players. And this scenario that we'll write down now is a scenario that Robson had also, but he discussed a slightly different question, which I will come back to. So the game now is like this, that in stage 1, each of them has to choose a pure mixed strategy to use in the game G when they play it. That's stage 1. In stage 2, there are 3 disjoint events that can occur. With high probability, nothing happens, and then they get the payoffs from the strategy they've chosen. With a low probability epsilon 1, player 1's strategy is discovered by the other player. And then the other player can choose any strategy for the game G to be played as he or she likes. And then the payoffs will depend on sigma 1, what was chosen by the guy who was discovered, and the new strategy used by the other player. And likewise, with probability epsilon 2 small, player 2 strategies is discovered, and then player 1 is free to change his or her strategy when seeing that. So that is the game. And what is then a pure behavior strategy in such a game? Well, it is a choice of a mixed strategy to use in the game G in the first stage, sigma I, and then a function, a rule that says if I am allowed to see the other guy's strategy and I can change now my strategy, what would I choose? So it's a mapping from the other guy's mixed strategy simplex to my mixed strategy simplex, right? Fi. So that is a behavior strategy. Now, one can say that the behavior strategy in this game implements sigma hat, a given strategy profile sigma hat in the game G, if it is the case that that is the outcome in all these 3 scenarios. So nature will choose in which of the 3 scenarios it is, and then if that is the outcome, sigma hat, in all of them, we say then it implements the strategy profile there, implements this strategy profile sigma hat. And then the result then that we have here is to say that if you look at the Nash equilibrium of a finite 2-player game, and then this will be detection stable if and only if, for all epsilon that meet these conditions, there exists a subgame perfect equilibrium that implements it. Okay, so it's the same thing as saying that there exists a subgame perfect equilibrium where this is what is going to happen. Okay, so that's a necessary and sufficient condition. Okay, so if we now take the criterion, the definition, and apply it to zero-sum games, we had matching pennies, and we found that that was detection stable. It's easy to generalize that to any zero-sum game for the intuitive reasons, the same as for matching pennies. Now, one can go further because it's not important that the sum of the payoffs is a constant or 0. It's just that they have conflicting interests. And there is a definition then going back to Dan Friedman, 1983. It says a 2-person game is strictly competitive if whenever player 1 prefers one strategy profile over another one, the other player has the opposite preference. Anything you want to say? Maybe.
It's different.
It's almost strictly competitive.
Oh, it's almost.
He has almost strictly competitive Aumann. We talk about several versions of strict competitiveness, and this is the one we use now. But you're right, Aumann had an idea, and it's called almost strictly competitive. Yeah. And that doesn't work. Our theorem doesn't work there, and we talk about that in our...
So it's a weaker version.
Yes, it's a weaker version. Okay, so if we take this one, then it is not so hard to show this, that all equilibria then are detection stable. Okay, so you have a reason to hide your your strategy. Now, potential games is another important class of games, and we take the definition here of a weighted potential game from the paper by Mandeville and Shapley, which essentially says that if you have a game and it is of the following type, that if one player I changes pure strategy from SI to S prime I for any given strategy profile for the other players in an n-player game here now, and you look at the payoff difference, that can be written as a difference of a potential function P, which is the same for all players, between these two situations, possibly multiplied with a positive constant Wi, some weight. Okay, so these are weighted potential games, if you can find such a function P. Now, and then one can show that if G is a weighted potential game, then exists at least one detection stable equilibrium.
Does it maximize the potential?
Exactly. I mean, this is the intuition is exactly right what you say. So if you look at games with identical interests, so they all agree about everything, then there's the best strategy profile. Then, of course, that is detection stable. And then you can weaken that slightly by going this way. So this is following.
Things that don't maximize the potential are necessarily not detection stable?
No. They can be. So I have examples where you have several such. That's possible. But this is just to say that we can guarantee existence at least in this class of games, but not generally. Okay, so now I'm reaching the end of the talk, and just recall that it might be natural to introduce randomization in zero-sum games. That was suggested by Borel already and von Neumann. And while this is not, randomization is not natural at all in coordination games, you would rather like to avoid miscoordination. And then we asked here, what are the incentives? And we focused then on the case of possible detection of your strategy, right? And define the concept for that. And we show these things that you just saw. We can think of it as a subgame perfect equilibrium in a spying scenario where you put in the game as a part of the bigger game. And that we have these results I just mentioned. And then we are still working on this, so please let us know if you have suggestions or comments to this work. So it's still ongoing, and we haven't solved all the problems we have been approaching yet, so we are grateful for comments. Yes, please.
So an intuitive generalization is that coalition group right here basically is the deviating profile is actually stable itself, because here you don't consider the
exactly
profile
right.
Stable.
Yeah.
Generalize it.
That's a very interesting generalization, yeah, right. So there are several ways one can do about this. There was so little done here, so we thought we wanted to sort out the basic things first. And so what we do more, and I didn't talk about here, is that we look at the invariance properties. If two games have the same best reply correspondence, do they have the same set of detection stable equilibrium? No, and so forth. So invariance properties, and we show the relationship to Rosenthal's notion and also to Robson's notion, and Rosenthal's notion is stronger because it was like you can commit yourself to a mixed strategy, and we cannot do that here. So that's a more stringent requirement. This is a weaker requirement because he asks for a revelation of the realization of a strategy, and also he asks for approximate implementation. So you should be able to approach it by letting epsilons become smaller and smaller. So that is then weaker in that sense. Now we do have notions of strong and weak detection stability, and we are still working on one of them to see if we can come closer to Robson's idea than we are right now. And a final comment that we note that this idea of detection stability can be added on to any refinement you like. So one could also, of course, so I mean, if you have something like, say, Rita talked about, which has a lot of nice properties, we could say, well, we might want to also check if it's detection stable or not. And I would argue that in many situations, if it's detection stable, it's more plausible, I think, as a prediction than not. So that's the end. Thank you.
So I have a basic objection. I mean, it's the following. I mean, in the Marshall-Aumann example, this arises in the context of inspection games. There's a power to inspection games, where there's a natural advantage to committing to be able to have the power to commit. Meaning you get a higher payoff when you are able to commit to a strategy. In this case, the mixed strategy that goes a little bit to the left, where they induce the behavior of the player that maximizes your payoff. So I see exactly this case. So if you commit to a little bit to the left, you get something better.
Yes.
So I say in every situation where you have this power of commitment, you actually have exactly what you don't have inspection and stability, in the sense that in that case you want to be found out, because that's the kind of commitment, and then you induce a better behavior to you. So I think it's always natural to see that commitment helps you, except in zero-sum games, obviously. And therefore, whenever you have a power of commitment, you have exactly a failure of detection probability, of your concept. So I think your concept exactly fails where you have the power of commitment. That would be my conjecture.
Right.
Yeah.
No, that's an interesting question. When you look at this game, it is such that you would like to use a strategy, and it should be observed by the other guy, which is slightly below the equilibrium.
Exactly.
But there is, in the continuum case here, there exists no such best choice. You can be approximately, you cannot get the top unless you expect that the other guy is indifferent and then will play to your favor. And that's what Robson did in his assumption. He assumed that when there is this indifference that the other guy will play in your favor, and we see no reason for that. So what I would say in this case is that with the continuum here, there is no best thing for me to do if I would know that the other guy would not observe what I would do. I would be arbitrarily close to 0.75, but not there. And then one could think of discretization. One could say, suppose in practice, we have finite world, and we could say, if I have a grid there, there would be something that would be best. Yes.
There's even a more subtle argument. It says if the other guys would not best reply, despite being more different, you would commit to something slightly smaller. So in that sense, it's the only sub-imperfect equilibrium in the game. So there's a good reason to not just assume best behavior, but it's actually the only sub-imperfect equilibrium. Anyhow, you might know this.
Right. And what Bernard is talking about here is a weaker form, I would say, and that is what we have as our definition of weak, which is take limits of going, in this case, from the left. Yeah.
We have time for just a couple of questions. One in the back, and then.
So, your definition of detection stability is basically based on 2 rounds of best responses, right? So, yeah. I was just wondering if when it comes to generalizations, if you look at multiple rounds of best responses, does that make sense?
I don't know. It becomes very complex. This is the simplest case that exactly one player gets to have a revision possibility, or either nobody or one player only. If you have multiple observations and so on, that becomes extremely complicated, right?
Yeah, I guess.
Yeah.
I was wondering about the connection to extensive robustness by Huguet.
I'm sorry?
Extensive robustness by Huguet actually is asking that any extensive form survives any extensive form of a normal form game. So I was wondering whether you know the connection of the concept.
Once more, what was that? Can you
Your
say
concept
it once?
of extensive robustness, right?
What do you call it? Yes.
And extensive robustness is
I see.
when it survives any extensive form you can think of. That is when you go.
I don't know, but thank you.
Because it seems
one could look at that. I don't know.
There's another question in the back.
Thank you, it's very insightful. My question is kind of a follow-up on Bernard's question, which was that if you take the extensive form game seriously, then I think here what you actually would get in equilibrium is that you have to mix over mixed strategies, because you might be found out, in which case you want to have that mixed strategy up there. And then I think an equilibrium does exist where if you marginalize over the multiple mixed strategies that you're mixing over, you actually do get, again, the equilibrium strategy. But have you thought about these?
Yes, that is what is very close to what we do with the what we call weak stability, which we have not explored fully yet, but we are exactly where you are. And then one can the definition is then you can approach this equilibrium, right? By finding sub-imperfect equilibria, and you have to randomize over those behavior strategies and then regenerate this. So the question is also, what would one think would happen? If people play such a game, what would they do? Would they play the equilibrium? Armand Marshall says they wouldn't do that. They would play the max-min strategies, and that would be to play 1/2 instead. So they say, this is what player 1 would do, 0.5. And we No, and one could imagine this, one could imagine something else. So what do you think, Rita?
I have another question, perhaps. If I may. One question and one conjecture. The one question is: imagine you do your exercise, but you allow player to epsilon optimize. In this case, epsilon optimize. They optimize up to epsilon, their payoff. He may find my strategy, but if I lose only by epsilon, I don't care.
Yeah.
But then here you will restore existence here.
Exactly, right.
At least in this example. Is it true in general?
No, it's not true in general. So that, I mean, that is very much in line with this other idea. They go in the same direction. So one could allow for epsilon, epsilon best replies. Yeah. Now, if you would take a coordination game, that wouldn't work. That would still reject the mixed equilibrium. It would not reject
existence in the coordination game for other reasons. Because
yes,
of other
absolutely. Yeah, but that's correct. Yeah, one can think of that.
Secondly, can you prove, and I think it may be true, any -1 index equilibrium will be detection unstable? Because dynamically they're unstable. They might. I
know very well what you're saying, and I think I would, if we are to bet, I would bet on your side that probably that's true what you say. Yeah. I don't know if anybody wants to bet against Rida and me here, but
check any game, check any -1 index equilibrium, it will be detection unstable. That's the conjecture.
Possible.
Was that conjecture?
So, just to link our talks.
Shall we offer?